Hello and welcome back to the Academy of Anaesthesia. Today we'll be going through a very common topic that appears at least once a year in the exam, and that is temperature monitoring in anaesthesia. Being under an anaesthetic produces a situation where the body is very vulnerable to losing heat, and the detrimental effects of hypothermia can be fatal. Hence, why temperature monitoring in anaesthesia is so important. This will be a two-part series where in the first part we'll be going over the different methods of monitoring, the mechanisms of heat loss, and what the NICE guidelines suggest we should do to avoid hypothermia. The second part will be a clinical case in which a patient with hypothermia presents, and we will discuss the physiological implications and the management strategies to treat them. I'm not going to read out all the technical definitions of terms such as heat, temperature, Kelvin and Celsius, etc. because it will be a waste of your time. Instead, I'll leave them in the description below if you want to refer to them. In the primary exam, you are expected to be able to define these terms. For the purposes of this video, it's important to at least distinguish between temperature and heat. So to do that, think of a cup of boiling water and an iceberg. The iceberg is a lot bigger and has a lot more molecules and therefore has more total heat energy than the cup. However, if you touch the cup, heat energy is being transferred from the cup to your hand, whereas with the iceberg, the heat energy will be transferred away from you. This is because there is a difference in temperature. Temperature is therefore the likelihood for one substance to transfer heat energy to another. The higher the temperature of an object, the more likely it will transfer heat away from itself. To classify temperature monitoring methods, you can classify them into non-electrical, electrical, and infrared. Non-electrical methods include gas, liquid, solid expansion, and liquid crystal methods. The classic example of a gas expansion method is the aneroid gauge. Aneroid basically means there's no water in it. Here, the gas inside the gauge heats up, expands, and the pressure pushes the needle on a dial. The dial is then read. Although not used for temperature clinically, the principle of it is used every day to check the cuff pressure when intubating. Liquid expansion methods include the classic mercury and alcohol thermometers. When heated, the liquid expands in a closed cylinder, which then leads it to move up a calibrated scale. The advantage of using mercury over alcohol is that it has a higher boiling point and is more dense. It means for the ranges of temperature we are measuring, it's a better tool. It's not commonly used in clinical practice because it carries a risk to the environment. The last expansion method includes the bimetallic strip. This is commonly found in a lot of the vaporizers that we use, though there it is used to correct the amount of anaesthetic agent that mixes with the fresh gas flow. The bimetallic strip relies on the fact that two metals joined together with different expansion coefficients will bend in a certain way when heated. You can connect this to a pointer on a scale to give you a measurement of temperature. The liquid crystal method is not commonly used in anaesthetic practice, but I've included it here for completeness. Electrical methods include thermocouples, resistance thermometers, and thermistors. Firstly, thermocouples are two different metals, usually copper and constantan, which is an alloy of copper and nickel, that are in contact at two different points. One point is kept at a temperature that's constant, and that is the reference point. The other is subject to a variable temperature, and that's the measuring junction. It relies on the principle that when there is a temperature difference between the 2 points, it produces a small voltage, and this voltage is proportional to the temperature difference, and when measured, can be converted back to the original temperature value. This phenomenon is known as the Seebeck effect. You can draw a graph to represent this. Draw the two axes with temperature on the x-axis, in degrees Celsius, and voltage on the y-axis, in millivolts. Draw a straight line with a positive gradient that starts from above zero on the y-axis. This shows that as temperature rises, the voltage measured at the measurement junction of the two metals will be higher. The next electrical method is the resistance thermometer. This type of thermometer includes a thin metal wire, often made of platinum. When the wire is heated, the resistance increases. This is shown by this graph, where temperature on the x-axis, again in degrees Celsius, and resistance on the y-axis, measured in ohms. Draw a straight line with a positive gradient, again from above zero on the y-axis. Remember that when the temperature is at 0 degrees Celsius, the wire still has some internal resistance, so it's important to start the line above zero on the y-axis. Resistance thermometers are extremely accurate, but they're much slower than other methods. Last in the electrical section is a thermistor. This is a semiconductor which is made up of a heavy metal oxide. The relationship between temperature and resistance of a thermistor can be represented by another graph. This graph has temperature on the x-axis, again in degrees Celsius, resistance in ohms on the y-axis. Now draw a curve with a negative exponential. This shows that in contrast to the platinum wire, here as temperature increases, resistance decreases non-linearly. Thermistors are commonly found in cardiac output measuring devices where the change in temperature over time is measured to estimate cardiac output. A thermistor is also what's found at the end of an esophageal temperature probe, which we commonly used in anaesthetic practice. When I was revising for my final VIVA, I was told by an examiner who had more than 15 years of experience examining that even in the final you are expected to be able to reproduce these graphs, so it's important to practice them. Finally, the infrared method of measurement relies on the principle that the infrared energy emitted by an object is proportional to its temperature. A probe is placed inside the ear, and the infrared energy emitted by the tympanic membrane is measured. This is by far the most common method of measuring temperature on the ward and in the community. That's all the different methods of monitoring temperature. Next, we will talk about the mechanisms of heat loss perioperatively, which can be broadly classified into 3 phases and 5 methods. The phases can be represented by a graph which has time on the x-axis with temperature on the y-axis. The first phase, also known as the redistribution phase, is due to the fact that when a patient goes under an anaesthetic, the blood vessels of the body dilate, and that redistributes the heat and causes it to be more spread out and closer to the skin. This drops the core body temperature very quickly. Remember that heat and temperature are slightly different, so the heat energy of the body remains the same, but the temperature drops. The next phase is where the body loses heat at a steady pace because of the 5 main heat loss mechanisms. This usually happens when the surgeons are prepping the surgical site and the rewarming techniques are halted. Usually the temperature falls by about 1 to 2 degrees Celsius. The heat loss mechanisms can be remembered very easily with the mnemonic, "The Royal College exam room is cold." Using the first letters of each word in that mnemonic, you've got radiation, which contributes 40% of the heat loss, convection, which represents 30%, evaporation, which represents 20%, and respiration and conduction, which represent roughly around 5% each. Depending on which source you read, respiration and conduction are swapped around, but the examiner should accept any order as long as you have them both at the bottom of the list. To tackle heat loss in theatre, as a mini checklist exercise, you can go through the 5 mechanisms and see if each one is addressed. For example, radiation and convection are the biggest culprits, together accounting for up to 70% of heat loss. They are best managed by using forced air warmers and keeping the ambient theatre temperature as warm as is practical. During this phase, where the 5 mechanisms of heat loss are occurring, because the drop-off in temperature is linear, this second phase is also known as the linear phase. Finally, there is the plateau phase, or the third phase. This is when the body temperature falls to roughly around 34 degrees Celsius, and the body's own thermoregulatory mechanisms kick back in. You get vasoconstriction, and the heat loss from the body equals the heat produced, and so the temperature remains relatively constant. It is important to remember that if you've done a combined anaesthetic such as a GA and a spinal, this vasoconstriction is significantly impaired, and so patients with a combined anaesthetic technique will continue to lose even more heat and reach the plateau phase at a much lower temperature. To summarise, we've gone through the different methods of monitoring temperature and the mechanisms of heat loss. Now, let's quickly go through the NICE guidelines and see what they suggest we should do to avoid perioperative hypothermia. I'll mention the salient points and the interesting bits, but if you want to read the full guideline, I'll link it in the video description below. There are specific groups of patients that are particularly vulnerable to hypothermia, and these include patients at the extremes of age, such as neonates and the elderly, patients with a low BMI, patients with certain medical conditions such as burns or hypothyroidism, patients who have a combined anaesthetic technique such as a GA and a spinal, and patients who are undergoing prolonged surgery or surgery with an open cavity such as a laparotomy. Interestingly, the NICE guidelines suggest that for adults undergoing surgery, we shouldn't rely on a tympanic thermometer as a measurement method, as it gives an inaccurate estimation of core body temperature. Bit of a controversial point, as this is one of the commonest methods we use. The main part of the guideline is helpfully divided into preoperative, intraoperative, and postoperative measures. I've included the important points here which you can refer to. Pause the video and have a read of the main recommendations. For the primary, that is more than enough to pass the temperature question in a physics or clinical viva. Remember that with the recent push from the college to make the primary more clinically relevant, it's useful to have a general idea of what the NICE guidelines suggest. Stay tuned for part 2, where we will discuss the pathophysiology of hypothermia, how it might affect some of the investigations we perform, and how to manage hypothermia in the clinical setting. I hope you found the video useful, and thank you very much for watching.